Previously on this channel, I've reported on several space startups that plan to extract resources from asteroids. These startups can be divided into two categories. First, companies like Kármán Plus target asteroids likely to contain water ice. Water serves as a key resource for transportation in the solar system, since it enables production of water-derived propellants. The second category prospects for valuable minerals, such as platinum group metals and rare earths. Additionally, industrial metals like iron, aluminium and nickel support the construction of large structures in space. I recently discovered a paper that suggests a simple method for harvesting metals: blast mining. This technique is common on Earth, but can it succeed on an asteroid? The concept is simple, so I'll explain it briefly now, and then we'll look at the details in the rest of the video. The basic idea involves using shaped charges to blast a 100-ton slab of iron nickel free from the asteroid. A space tug pushes it towards Earth and gives it a spin for stability. Once it reaches low Earth orbit, following an aerocapture maneuver to reduce velocity, a spacecraft rendezvous with it and attaches a heat shield to the front of the slab and a parachute system to the back. Finally, the slab is deorbited, the heat shield absorbs heat and reduces the descent speed. When the slab's speed is subsonic, a parachute is deployed, slowing it down to an impact velocity of 500 to 700 km per hour. If aimed at the soft sands of the Sahara Desert, the slab would create a small crater measuring 4 to 8 meters across and penetrating 5 to 15 meters deep. A team retrieves the slab for refining and processing of useful materials, ideally PGMs and rare earths. That summarizes the plan. Now let's explore the details. Challenges in mining asteroids. On Earth, blast mining first requires drilling a hole into a rock formation before filling with explosives. Drilling on an asteroid due to the near-zero gravity would be extremely challenging and would require anchoring the drilling machine with a large mass. An alternative method needs to be found. The authors of the paper suggest a simpler technique: shaped charges as a replacement for drilling and blasting. Shaped charges are commonly used in weapons such as anti-armor missiles and in mining and demolition. These charges focus the explosive blast in a single direction, enabling deep penetration through metallic material. Exactly what you want when cutting through a metallic asteroid. Autonomous rovers on the asteroid's surface position the shaped charges to deliver precise, directed energy and break the rock into a desired shape. No drilling is required. If necessary, robots can place secondary liquid explosives into the holes created by the shaped charges for accurate and controlled blasting. Cutting out a solid rock monolith from an asteroid quickly could provide a scalable and commercially viable way to harvest material from it. This covers only the first part of the operation. Once a 100-ton slab of material has been liberated from the surface of the asteroid, it has to be pushed towards Earth. Let's examine that stage next. Mission planning, propellant consumption and asteroid rock size. The authors selected SpaceX's Starship as the vehicle for this asteroid mining mission. They chose it because it would likely become operational within a decade, offers a large payload volume, and significantly reduces the cost of sending mass to orbit. The authors calculated that a mining mission cannot be undertaken in the asteroid belt, so the metal asteroid 16 Psyche is just too far to reach, at least until propellant stations are available along the way. However, near-Earth objects or NEOs are in reach. The authors considered the best shape for a solid iron-nickel slab, ensuring it maintains a predictable center of gravity for reliable transfer to Earth and stable atmospheric entry without tumbling chaotically. In their assessment, a truncated square pyramid with a mass of 50 to 200 tons proves the most practical shape, balancing economics and re-entry characteristics. To maintain the center of gravity, the slab will be spun before pushing it towards Earth. The authors calculate a SpaceX Starship would need to burn between 40 to 60% of its propellant to get onto a trajectory towards a near-Earth asteroid and then decelerate and maneuver around the object. There would be enough propellant left to accelerate a 100-ton piece of the asteroid towards Earth. Alternatively, a space tug could be used to provide the necessary push. If the space tug uses water-derived propellants, it could sustain asteroid mining operations, assuming water is located and processed on the asteroid. Hydrated minerals appear on approximately 35% of all observed M-type asteroids, and for larger ones, those over 65 kilometers in diameter, up to 75% contain hydrated materials. A single Raptor engine burning at full thrust would accelerate a 100-ton block to 18.3 meters per second. Within 30 seconds, it would be traveling at 539 meters per second. That is twice the delta V required by OSIRIS-REx, the NASA spacecraft, when it fired its engines to leave the Bennu asteroid and head back to Earth. Feasibility of asteroid mining. M-type asteroids, where the M stands for metal, are composed of up to 80% iron and 20% a mix of nickel, iridium, palladium, gold, magnesium, and other precious metals such as osmium and rhodium. Many precious metals on Earth, due to their mass, have sunk into the mantle and core and are no longer accessible. These metals can be mined and extracted from nearby metal asteroids. Astronomers have identified several near-Earth M-type asteroids. For instance, 3554 Amun has an estimated diameter of 3.3 kilometers. The asteroid 1986-DA measures 3 kilometers in diameter and, based on its radar brightness, likely contains 100,000 tons of platinum group metals. While predicting the exact amount of material needed to return to Earth for practical asteroid mining is difficult, scaling up the operation clearly boosts chances of creating a viable commercial operation. Returning 100-ton slabs independently, without the use of a spacecraft, is a way of scaling up the process and moves the needle towards viability. Starship or other suitable heavy lift vehicle would be needed to send large quantities of shaped charges, liquid explosives, and additional or replacement autonomous rovers. A separate space tug, ideally refillable at the asteroid, would provide the push towards Earth. It also includes a mechanism to spin the slab for stability during its journey. In the case that water-derived propellant cannot be processed from the asteroid, an alternative is a simple mass driver engine. This involves accelerating small iron-nickel pellets from the back of the asteroid to provide thrust. These could be accelerated by an electric field to high speeds, providing the necessary thrust. Effects of a 100-ton impactor on Earth. Landing in the soft sands of the Sahara Desert poses minimal risk, as the area lacks population and the sand cushions the impact. The impact energy is roughly 1 to 2 gigajoules, equivalent to 230 to 450 kilos of TNT. The primary effects of the impact would be highly localized due to the soft sand. Based on penetration models and experimental data, the diameter is likely to be around 4 to 8 meters wide. The maximum depth of penetration is likely 5 to 15 meters, assuming a contact area of 5 square meters. The slab would come to rest 5 to 10 meters below the surface with possible fragmentation. No melting would occur due to the heat shield on re-entry and the modest impact speed. Sand and dust would be thrown outward, creating an ejector blanket of 50 to 100 meters in radius. Ground shaking would be equivalent of a magnitude 2 to 3 earthquake. This might be felt as a mild rumble up to 1 to 2 kilometers away from the impact zone. No shock waves, no structural damage. Any overpressure would be insignificant beyond 10 to 20 meters of the impact, equivalent to a strong gust with no risk of injury or damage. Immediately after the impact, the slab, due to friction heating, would be warmed to several hundred degrees Celsius, but no fireball or ignition of materials would occur. If the area is cleared, there is zero risk to humans. In short, the impact would be low risk and the slab could be easily recovered for processing. Concept of operations for an asteroid mining mission. Let's examine the process of blasting a 100-ton slab from a metallic asteroid. First, the excavation perimeter is outlined as can be seen in the graphic from the paper. You can see a Starship vehicle in the background, which provides all the shaped charges and autonomous robots needed for the operation. In the center of the monolith or slab, 2 holes will be blasted to affix anchoring rods. Software calculates the precise placement and inclination angles for the shaped charge explosives. Rovers position the charges at these calculated locations and angles. The detonation blasts the rock monolith cleanly from the surface, causing it to float above the asteroid. Controlling the position of the free-floating monolith can be done using cold gas thrusters and a control unit. The space tug rendezvous with the monolith and securely connects to the anchoring rods. The tug slowly accelerates the monolith and spins it up to stabilize its center of gravity. before releasing it once it achieves the necessary delta-V to rendezvous with Earth. The space tug refuels and prepares for the next monolith. Steady arrivals of starships with shaped charges, plus additional or replacement autonomous rovers or other equipment as needed. A space tug or spacecraft in low Earth orbit docks with the monolith after it has completed an aero capture maneuver and entered low Earth orbit. A heat shield and parachute system are placed on the monolith to prepare it for Earth re-entry. In terms of the heat shield, Atmos is developing an IAD or Inflatable Atmospheric Decelerator and recently launched a test version earlier this year. This system is low cost and is designed to safely decelerate cargo entering the Earth's atmosphere. Unfortunately, their current system, which is sized for 100 kilo payloads, cannot deal with a 100-ton payload. Even future upgrades will be very unlikely to deal with a massive rock monolith. The author suggests that even if the heat shield survives only for a minute or two during re-entry, it can help reduce the initial speed and maintain the proper angle of descent. Adding a parachute system at the back allows the monolith to slow down to a speed that keeps it intact and minimizes issues at the impact site. Iron-nickel monoliths do not need heat shields, as they can reach the surface intact. The paper mentions the Hobart meteorite that landed in Namibia, weighing 60 tons. However, the heat shield makes the landing site more predictable and reduces the chances of fragmentation. Dust and debris management. NASA, as part of the Artemis program, is actively working on dust mitigation strategies. Planners for an asteroid mining mission will have to use some of those systems. To deal with large boulders or rocks from the blast causing problems, a net could be fixed over the surface. This isn't to stop the boulders entirely, but to reduce the velocity of ejecta, resulting in them eventually coalescing back to the asteroid. Challenges and criticism. This study assumes master orbit costs will be much lower with Starship. We have no idea how much SpaceX will charge for Starship launches, and even if the cost of launching master orbit drops, it doesn't follow that the price SpaceX charges will be lower, as they will want to recover the substantial cost of development and will likely have a monopoly. I've concentrated on the technical issues with this study, but the legal side can't be ignored. How many countries would permit a 100-ton iron-nickel slab to descend unguided onto their territory? If the parachute system failed, the amount of damage that would be caused on the ground would be much higher. Many unknowns about the ability to use explosives in a vacuum and on how the asteroid material would be affected. Dust and debris add to the difficulty, while dealing with robots that are placing explosive charges in a near-zero gravity field amplify the challenges. Final thoughts. SpaceX's Starship Super Heavy launch vehicle and the expected reduction in launching mass to space makes the idea of asteroid mining more realistic than ever. Blasting a slab of material from a metal asteroid and sending it to Earth for an independent entry and landing simplifies asteroid mining operations. Terrestrial mines face low yields, which increase mining costs and reduce returns, even as consumption continues to rise. Materials such as zinc, nickel and tungsten could become exhausted within a century or less. M-type asteroids offer a virtually unlimited supply of materials, simply waiting in space for the first entrepreneurial startup to harvest them. Shaped charges have been used successfully on Earth for mining, although more study is needed on their effects on asteroid material in space. What do you think about the feasibility of blast mining on asteroids using shaped charges? Could this really simplify space resource extraction? Or are there major flaws in the concept? What do you think of the idea of landing 100-ton iron-nickel slabs in remote deserts like the Sahara, considering the potential risks and benefits for global metal supplies? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space news video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. I recap the videos I posted this week, answer questions, respond to comments and chat messages, cover any missed news and preview upcoming content. I'd love for you to join if you can. Be sure to like and subscribe so you will see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.